and dust with a very unique and special isotopic composition that's different than the average that we have here in the solar system, which represents the contribution of many different stars. We're trying to measure the isotopes in these meteoroids that have hit the spacecraft. What we're looking for, and we know they exist from work that's been done in the time since LDEF went up, what we're looking for are little grains that are so isotopically different than the average that they must have been formed around other stars at a much earlier time. We're looking for stardust. That sounds romantic, but it's true. Now, let me talk about my experiment, our experiment. And I had the first view graph, please. This shows the basic idea. These micrometeoroids are very tiny objects, and the basic experiment consisted of a very thin plastic film, and not shown on this view graph is the fact that we had covered the plastic film with gold palladium on the top surface to protect it from the atomic oxygen. Gets penetrated, the micrometeorite explodes, produces a cloud of vapor and debris, redeposits on the underside of the plastic foil, and that's the stuff that we analyze in the laboratory. Now, we can have the, I don't know how this is going to work. Let's try it. I have here, oh, that's going to show up on the screen. Anyway, in my left hand, I have a very thin piece of plastic that gives a uniform reflection. In my right hand, your left, you can see what's underneath the plastic, namely 4 squares of germanium. And we could see these 4 squares on a number of the cells that we had put up in space. There's some 200 of these cells, the combination of the plastic over the germanium. I have the next view graph. We could see the 4 squares, lines. We could see tatters of plastic, so that's the bad news. For example, you can see tatters of plastic. If you look on the top row in the right-hand corner, I think you can see the little shards of material. If you look in the first row, all the way down at the bottom, next to that golden thing, one up from the bottom, that's an intact cell. You'll have to take my word for it, but there are 11 intact cells on that setup. So the bad news is that any of the cells didn't make it. The good news is that some did, and a statistically significant number. Also, good news is the fact that we can analyze many of these cells, we believe. If the plastic stayed on during much of the flight, we think that probably is the case. Furthermore, another piece of good news is, of course, that LDEF is very big, and there are lots of impacts all over the place. In fact, one of the biggest impacts, irony of fate, if we could have that view graph back, you won't be able to see it very well. But anyway, on the view graph, on the metal rim, about 1 centimeter or less from our experiment, which is designed to study micrometeoroids, you have one of the biggest impacts that occurred. Nature might have cooperated by moving over 1 centimeter, but she didn't. In any event, there are many of these impacts all over the spacecraft. The LDEF scientists who initially put up experiments to study a variety of materials properties are cooperating with the meteoroid community and donating their materials. They're being documented right now, and donating the materials so that we can give a detailed analysis in the laboratory. We've been selected to have an experiment on the space station, which is the next generation of cosmic dust experiment where we actually measure the trajectories of the particles and then capture them and measure their isotopic compositions. That'll distinguish between dust from comets and asteroids. Part of the design at the moment are thin plastic, metallized plastic films, the kind that didn't take it, or at least totally, during the LDEF exposure. Quite clearly, we have to understand what happened and correct for that, and I'm sure that we can. But it simply illustrates how the evolutionary nature of the process of space experimentation, you do one thing, you learn, you build on that experience. And we'll build on that experience for the space station. I'd like to underscore the fact that visual observations, even with a pair of field glasses at 6 feet, are no substitute for getting materials back in the laboratory. I've worked for many years on lunar samples. We have a lot of them in our laboratory. The typical reaction of the layperson to a lunar rock is that it looks like a rock. It's not particular, they're vaguely disappointed. And that's true. Just looking at something, you really can't extract much information. But if you put the rocks in very fancy instruments, then you can extract information like the age of the moon, the age of impacts, all kinds of stuff that you can't see with the naked eye. So it's instruments, the extensions of the scientist's hands and eyes, that make possible the extraction of the information. And in the case of the lunar samples, it's taken 20 years, more than 20 years now, to arrive at a pretty general consensus as to the origin of the moon. Now, the analysis of LDEF won't take 20 years, possibly, but it will take some time. And we're looking forward very much to the analysis. Thank you.
Thank you. The type of orbital debris that's of interest to LDEF is that debris which is generated as a result of satellite breakups or the deterioration of spacecraft surfaces. There have been about 100 satellite breakups in orbit and creating a large amount of debris, and LDEF itself acts as an example of a deterioration of surfaces that produces orbital debris where small particles were observed to come off of LDEF during the retrieval process. Because all of these particles are traveling in different directions, they will run into spacecraft at very high velocities, average around 6 kilometers per second, and they will create phenomena very similar to meteoroids. They will create craters. They will look very much the same. However, and there are two ways, though, that we can tell them apart. One is they will be in different types of orbits, and therefore there's a certain directionality associated with orbital debris that is different from micrometeoroids. And secondly, by looking at the chemistry, as Dr. Walker has suggested, we'll be able to tell the man-made component from the natural component. Since we haven't done any chemistry yet, right now we can make some what look like some pretty good guesses as to where the stuff is coming from based on the directionality. I'll have the first slide, please. This is a computer-generated picture of what the Earth would look like from 15,000 miles if you could see all 7,000 cataloged objects that the U.S. Space Command is tracking. It is basically uniform around the Earth and within a distance of around 300 to 1,000 miles altitude. We expect that the smaller fragments, these things coming off the spacecraft, will have similar types of orbits. And because they have similar types of orbits, we can calculate then what kind of directions we would expect them to come from. And the next slide tried to illustrate that direction, where we would basically, if you think of yourself as sitting on LDEF or standing on LDEF with facing the direction of motion, most of the particles would appear to be coming from your left and right forward directions for orbital debris, with the more higher velocities coming from the more forward direction and the lower velocities coming from the side. This would mean then the front-facing surfaces would be a lot more heavily pitted than the side-facing surfaces, and a very small fraction of the material, less than 1%, would be on the rear surface. Because everything is moving in a plane parallel to the Earth's surface, there would be very few impacts on the top or bottom. Meteoroids, on the other hand, are part of the interplanetary environment. There would be nearly as many impacts on the top surface as there would be on the leading edge surface. But however, because it is moving forward, there would still be more impacts on the forward surface than the rear surface. About 10% of those, as many on the rear surface as the forward surface. This is basically what we observe on LDEF. That is, that we are seeing about a 10 to 20 to 1 ratio of front to rear surface impacts. We are seeing nearly as many impacts on the top surface as the forward surface. Therefore, you could conclude from that what we're seeing is mostly meteoroids from the craters that are of a size that you can barely see with your eye. However, there's enough uncertainty in this that there could be still a significant debris component, but we have to wait until we get to the chemical analysis to be able to make that differentiation. The next slide shows what we expected in terms of number of impacts on LDEF, and what we expected at the limit of threshold of what we can see with our eye, which is about a size of a hundredth of a millimeter impact, something the size of a grain of salt, or would make an impact roughly about a half a millimeter or so in diameter on LDEF. And what we expected was about a couple of thousand meteoroid impacts, but only about 500 orbital debris impacts. So this is consistent with our pre-mission model. We got this model from looking at recovered surfaces like Solar Max, and so there isn't any real surprise there. We expected more meteoroids in this particular size regime. However, as you go to larger sizes, we expected more of a debris component. The largest particle that we expected on LDEF was something of the order of about a 1 or 2 millimeter impact, making a crater something of the order of about a half a centimeter across if it hit aluminum surface. With one impact, you can't do much statistics as far as directionality, so we can't really say whether there's orbital debris or not. We'll have to wait for the chemical analysis to determine if that's a true picture. We also, for larger impacts, we only had about one chance in 100 of being impacted by something as large as a centimeter, which is what the space station habitation modules are concerned about, and it looks like we didn't get that impact. We also did not get an impact of something that was cataloged, obviously, which was of the order of 1 chance in 10,000. So we can conclude from LDEF that there's nothing in disagreement with what we expected as far as orbital debris is concerned. There are no surprises, but this is only after a superficial look at LDEF. We'll have to do much more analysis to be sure. So in conclusion, we can conclude that the orbital debris environment is not any more severe than we anticipated, but we need a lot more analysis to be sure of that. There is one strong conclusion that we can reach, and that is that there is a very marked directionality to impacts, especially meteoroids, that will help save shielding as we design the space station.
Thanks, Brad. We go now to Jim Adams.
Yes, I'm the principal investigator on the Heavy Ions in Space experiment on the Long Duration Exposure Facility. If I could have the first view graph, I'll show you the location of our experiment. It's on the space-facing end of the vehicle. Our experiment is to measure cosmic radiation. You can see it's located in the two trays, which are circled in white on the spacecraft. The experiment is intended to measure the heavy ions in cosmic radiation. Cosmic rays consist of protons, electrons, and the nuclei of the atoms of all of the known elements of the periodic table. These particles are traveling at very high velocities in space, and we collect them in this experiment. And in particular, we look at the heavy elements, elements of at least silicon in the periodic table, and heavier in this experiment, concentrating primarily on the elements above iron. If I could have the second view graph, show you a little more about how the experiment is designed. Our intent is to measure the composition of cosmic radiation so that we can determine the elemental composition of the various samples of matter which are present in cosmic rays. We now know that cosmic rays come from at least 3 distinct sources. The highest energy ones come from all over the galaxy and give us a sample of the composition of our galaxy. At lower energies, there is a component which comes from the very local interstellar medium, that is the material lying between our solar system and the nearest stars, the medium lying out in between the stars. That material is unique because it's singly ionized, and using the Earth's magnetic field, we can separate that component from the others. We know that during solar flares, solar energetic particles are accelerated, and we have the opportunity to examine this component of radiation as well. We're interested in particular in learning the charge state of solar energetic particles in this experiment. Now, the experiment uses plastic track detectors to detect these cosmic rays. So if I could have the next transparency, I'll show you a picture of tracks which have been revealed in these plastic sheets by chemical etching. The sheets record the tracks by the radiation damage of the particle as it passes through the sheet of plastic, and that damage is revealed by chemical etching. The etch pits which are shown here are due to a laboratory radioactive source emitting alpha particles, and they are among the smallest tracks that we would expect to see in LDEF. So you can see these pits can be made quite apparent from the surface of the detector material. Now, we're asking a lot of this detector material. Not only must it record the passage of these particles reliably and accurately, but it must store that image for, in this case, up to 5.5 years. To make the detector perform that function reliably, we need to have rather good temperature controls. We also have stored much of the detector in the experiment inside a sealed container. Only the small stack on the top of the experiment is in vacuum. Now, if I can have the next transparency, we will see a picture of LDEF as it appeared just before deployment. This is as the spacecraft is being removed from the cargo bay. And you can see, again, our heavy ions in space experiment. It arrived in space in very good condition, and in fact looked in good condition when we last saw it drifting away from the space shuttle in April of 1984. Now, if I can have the next view graph, we'll see what it looked like as it was being returned to the cargo bay for retrieval. The thermal insulation blankets on top of the experiment have come loose and rolled up. Now, I'd like to point out some details since I've had an opportunity to look at this up close. Underneath these thermal blankets is the top stack of Lexan track detector, and that's the material that you see exposed here in these locations, as well as in these up here. 7 of the 8 modules are identical in design. The 8th module differs in that stack of detector, which is on top, and these modules has been moved inside, and the lid of the module has been replaced by a much thinner window, and we needed a supporting member here, so there's a metal cross over the top. And this is a Kapton window here, which appears to have survived, even though the blanket peeled up in this region, exposing it to the sun. On close examination, the blanket consisted, it has a structure rather like a quilt. And the batting of this quilt consists of aluminized mylar and a polyester net, similar to bridal veil. And the face sheet of this quilt, in this case, was a 5 mil Kapton sheet, which was painted with white paint on the outside. The blanket was fastened on by means of a silvered Teflon tape around the edge. And on close examination, we could see that this tape had torn, allowing the blanket to come up. In all of these instances except this one, in this case, the top face sheet, which is made of Kapton, tore right across the middle. There seems to be, we had initially suspected that we might have an adhesive failure, and there doesn't seem to be much evidence for that now. There's clearly the failure is a result of the material being torn. We don't know what caused the material to tear. We've not had an opportunity to do any pull tests on the material, so we don't know if it at present has its original strength or whether the strength of the material is much, much lower than we'd anticipated, and that caused the failure. We have some ideas about what might have caused it, but none of these are consistent with the data that we presently have. So we'll have to return these blankets to our laboratory and investigate further what caused the failure. We have removed some of the blankets. For those of you who've had an opportunity to see the spacecraft, you'll see that these trays have now been covered. And that's because we had to remove several of these blankets in order to make it possible to rotate the spacecraft so the other experiments could be observed. And in removing the blankets, we exposed portions of track detector, let's say in this region here or here, which had not previously been exposed to sunlight. Even the lights in the room in SAFE 2 can alter the tracks recorded in this detector material, and so we put the covers on in order to preserve the data that may still be in these. As I mentioned, thermal control is important for the track detectors, and so we're quite concerned about the data that may have been lost in these modules. We think we're rather lucky with this module here because even though the face sheet of the blanket split, the batting or core material of the blanket stayed in place. There are about 15 layers of it, and while the first couple of layers have been damaged and eroded away, the remaining layers are in place, and we expect this blanket may have performed close to our original expectations. So the temperature control for that module may not be that different from what we had planned. but it probably is quite a bit different in the others. When we get the modules themselves off the spacecraft and return them to our laboratory, we'll be able to see how the track detector performs by looking at components of the radiation environment, which are well known, to see if they have been measured correctly by the track detector. Until we do that, we won't know how much data has been lost. And that's the status of our experiment at this stage.
Thank you, Gene. The SEEDS experiment that we call Space Exposed Experiment Developed for Students, or SEEDS for short, is a cooperative program between NASA and Park Seed Company of Greenwood, South Carolina. The experiment consisted of placing 12.5 million tomato seed in 5 canisters aboard LDEF in such an arrangement that they were exposed to the radiation of space but protected from the vacuum of space and also the temperature of space. We plan to distribute these seed to students in classroom situations across the country sometime about mid-March. The main thing that we're doing is trying to encourage interest and enthusiasm in the sciences among the students of the nation. And as they evaluate the seed, they'll be looking for such things as germination rate, growth rate, mutation rates, and these types of things. Also, the experiment will provide some insight into the survivability of seed in a space storage facility. Also, from a plant breeding standpoint, it'll give us some insight as to using space environment as a breeding tool. About 90,000 kits so far have been requested by teachers. The kits will contain a control sample of seed, a flight sample of seed, some informational material concerning the experiments that we would like to see done, and also a data retrieval information packet. We still have about 60,000 kits available and will be distributed on a first-come, first-served basis. If there's teachers that have not requested seed and are still interested in having their classes participate, we would like for them to write to NASA Seeds Project, code XEO, NASA Headquarters, Washington, D.C., 20546. Let me repeat that. NASA Seeds Project, code XEO, NASA Headquarters, Washington, D.C., 20546. The information that we need from the teachers to be able to process the request is we need a teacher's name, we need the school name and address, what level of education they're teaching, and how many kits they will need. And one kit will service one classroom. And then looking at the LDEF and the tray that's on it, the LDEF tray, or the seeds tray, is completely intact as far as we can tell. It has a thermal shield over it, so we cannot see the canisters that the seed are in, but the thermal shield is in place and looks good. So knowing that, it appears that the hardware performed as it was planned, and the seed have been protected from those things in space that we intended to protect it from. Also, our control seed is still very strong. It's germinating at about 75%, which is good for a seed that's approaching 10 years old. So from these two things, we expect that we will have between 2 and 4 million students in the spring semester conducting a very interesting and a very exciting experiment on these seeds. Thank you.
Thank you very much. We will take questions here at KSC before going to other NASA centers. Please wait for the mic and give your name and affiliation. Any questions? Jim? Joe? Oh, that's all right. That's all right. Just go ahead.
Phil Chen of Earth News. Bill, you told us before that LDEF had come back in excellent condition, everything else, and you could have another bunch of trays ready to go almost tomorrow for new materials that have been developed in the 15 years since LDEF-1 was first conceived. Any idea on what you'd want to do? Any chances of flying LDEF again? And if not LDEF, how about other free-flying platforms like Eureka for having reflying materials which haven't come out perfectly this time, or new materials?
Well, as you've heard, some of the experiments on LDEF have weathered But the facility itself, the aluminum structure, is in excellent condition, and yes, it could be reflown again. We have no qualms about that. NASA has no plans at this point in time for a reflight. I think the kind of things that we would hope for is that this LDAF mission will illustrate the kind of return that you can get from these types of experiments. This LDAF mission was a very effective, very cost-effective research program. In regard to the kind of things that you would fly, I think the materials people and the science people here have learned a great deal, and they would dearly love to get a chance to make improvements, to put new generations of materials up and see how they work. We're approaching a point of making some final decisions on space station materials, and I think it would be very effective to be able to put these materials up on a spacecraft like LDEF and get a little survival data prior to committing to the space station.
Jim Banky.
Jim Banky of Florida Today. I have two questions. One for Bill. Maybe you could summarize on behalf of the whole team what perhaps has been the most surprising or exotic find on LDEF since you've had a first chance to look at it. Then I have a second question.
Well, see, I think I'll open it up. Would anybody on the team like to comment on their biggest surprise?
Well, I think probably our biggest surprise is going to come when we have the experiments back in the lab and we can really examine the condition of these materials. Certainly, to me, the ultraviolet environment somewhat surprised me in its intensity and the changes it could bring about on materials.
I think the thing that we've seen on LDEF are no individual spectaculars, but we have seen a wealth of detailed evidence of phenomena that takes place in space that is going to be very crucial when it comes to designing a spacecraft that has to function for a long period of time. And as Bob Walker pointed out, when it comes to designing experiments that have to function in space.
The second question, it had been said earlier that LDEF had proved that Space Station Freedom certainly could survive up on orbit. But I'm wondering, has anyone concluded yet if Space Station Freedom can last as long as we predict? Will things like the solar blankets need replacing any sooner or any longer? How long will it last now, based on what your findings are?
Well, I think it'll be a little premature to give you a number on that. Certainly, there are some things that we have to look at closely and design around or use different materials.
Any others in the back?
Muriel Schloss, Teacher's Laboratory. For Jim Alston, is there a minimum grade level for the SEEDS experiment?
Well, we had originally set it up for grades 5 through university, but now as we see that we've got kits going, or kits left, any grade is being accepted now.
Stand up. Dan Billow from WESH-TV. For Mr. Kessler and Mr. Walker, both of you. Mr. Kessler, or is it Dr. Kessler? You mentioned a concern with objects the size or greater in size of a centimeter with the space station. What's the concern, and are there any out there? Well, I mean, what would happen? How much damage would that do? And do you think, and maybe both of you could address, what is the greater concern, space debris or naturally occurring meteoroids?
The 1 centimeter threshold for the space station comes about because you want a safety factor when you fly the space station for the habitation module. That is, you can't accept one impact every 6 years. Because you have man on board, you're going to design it so that you have something of the order of 1 chance in 100 to 1 chance in 1,000 for a comparable period of time. When you look at what we expect and what we've also measured from ground radar, it puts the orbital debris environment as being the dominant factor in designing to the habitation module for the space station. And that means adding extra shielding, and so in order to get it to this level of safety required. But when it comes to maintenance kinds of activities where you may have to go out and replace something because it got penetrated, meteoroids may well dominate. And so it's a trade-off as to which is more important. It depends on where you are on the spacecraft and what it is that you're trying to protect.
Yeah, I know the score of that. It's the size. If you got hit with something like that, traveling 6 kilometers or 8 kilometers a second, it's very difficult to protect against it. The chances of getting hit by a meteoroid that size are zilch at the first order. And there, the space debris dominates. Now, the chances, even with space debris at its current level, of getting hit with something that size is pretty small. But it's higher by far than getting hit by a meteoroid, and it would do a heck of a lot of damage. As you get to the very small things, then the micrometeorites dominate. But in order to protect astronauts and space stations, you certainly have things that you can do to protect yourself, like putting in a little bumper, much like our plastic films, where in going through the bumper, the micrometeorites disperse, and their effect when they hit something else becomes much smaller. So there are all kinds of things you can do, and it's not to panic. It's just that now with LDEF, instead of guesswork, you have facts.
Harry Colcom, Aviation Week. The other day, Dr. Kynard estimated about very roughly 10,000 impacts on LDEF. I wonder, in the past few days, has that number been refined?
Well, I feel confident if you look at a small enough scale, there are 10,000 impacts on LDEF. I'm very confident of that, and the problem when we come with numbers is where is the threshold that we're talking about? Are we talking about things that we would take an electron microscope to find, or are we talking about things that we would see with our eyeball? I suspect that there are thousands of impacts on there that are visible under careful lighting with the naked eyeball.
Bill Harwood, do you have a question?
Bill Harwood, UPI. Don, the model, the graph that you were showing a while ago, the sizes of the impacts you guys are getting, how did all of that meet with what you expected? Any cause for any concern whatsoever down the road? Easy to protect against what you've been seeing?
Not so far. It's easy to protect against everything that we're seeing so far. The largest impact, for example, a millimeter, a spacesuit would be vulnerable to that size. But again, you can be safe against that either by adding extra layers onto a spacesuit or limiting the amount of EVA time to a few hundred hours per year, and then you can have the same safety that you would have here on Earth from comparable driving for a year. So, but when you get into larger sizes, larger than about a millimeter, where you run into the probability as opposed to a frequent type of phenomena, then you have to start adding shielding. And right now it's baseline, for example, the habitation modules for the space station to add about 2,000 pounds per module of extra shielding. We don't have enough information right now to know whether we need to add more than that or not. And for that reason, we have under development with an agreement with MIT and the Air Force to build a ground-based radar that will statistically monitor this centimeter environment.
I think I just missed this. I'm sure Jim Austin said that. When do the seats come off and go back to you guys and then get shipped out?
All right, they're scheduled to come off on February 21st, and we'll be carrying them back to our facility on the 22nd.
Beth? Joe?
Beth Dickey with Reuters. I have two questions. First, Bill, when we were in SAFE 2 the other day, we started to get a definitive schedule from you on what exactly is going to be happening and maybe what the first 3 or 4 experiments off LDEF would be. I'd like you to go over that. And for Dr. Walker, if you would talk just a little bit about what exobiology is going to be done in terms of extraterrestrial life on LDEF.
Okay, let's see. We could give you a preliminary schedule after this conference on the removal of the trays. There are 86 experiment trays on the LDEF. We anticipate that the first trays will start coming off about the 20th of this month. The seed tray is one of the first trays that come off. The order of tray removal is governed by a number of factors. We would like we have to have access to certain trays, so it means before you can remove one tray, you have to remove another tray to be able to get in behind it and disconnect active cabling. There are some trays, for example, we'd like to have access to see the experiment initiate system early on, so we will be removing some experiments early to give us visibility to that system so that we can check that system out. From there on, it becomes one of which experiments are most crucial in terms of getting them back to the investigator and then letting them start their analysis.
Okay, I'm no expert on exobiology, but the organic molecular composition of comet dust is an extraordinarily interesting question, because there are some people that feel that the original organic molecule heritage of the Earth was largely derived from cometary material, which, as I pointed out, is what we think we're studying when we study at least a good fraction of the meteoroids. And there are people that have been here this last week whose primary interest is in exobiology, and we ourselves will be attempting to do organic analyses of the residue material. However, that's a very difficult game. You have to realize that an impact is an extremely violent event. These little particles are traveling many times the speed of a rifle bullet, so you don't really expect to recover very much intact material. Organic molecules are particularly sensitive to, of course, heat, pressure, what have you. So I wouldn't, in our experiments, anticipate that we will get remaining very much organic material. Nonetheless, it's a first-order scientific question related to the meteoroids, just a difficult question to tackle.
Any other questions at KSC? Okay, I understand we have some questions from Langley Research Center.
This is Art Franklin from the AB Mod in Virginia. I've listened to the briefing. It seems that the most important information we are learning about LDEF pertains specifically to space station freedom. Will LDEF be able to provide us definitive answers? What type of material is needed for that station, and what is
They're going to try again.
Seems like every question we've had to me.
What definitive information about LDEF will we have at this point in the building of space station?
We're going to go to NASA headquarters here in Washington, D.C. and see if the technical people can straighten out the problem at Langley. Okay, headquarters?
Yes, this is Jim Graham from Aerospace Daily. I hope I'm coming through a little bit clearer. I had three questions, one to Dr. Kennard and two to Mr. Kessler. The first to Dr. Kennard is, can you tell me how close the inspections have been of LDEF so far? I heard at least one or two people say they were standing about 6 feet away looking at it with field glasses. Has anybody gone up close to it yet?
In general, they have been back somewhere between 3 to 6 feet away, and a lot of it depends on where the experiment happens to be on the facility as it's rotated around. There have been some instances where people have had an opportunity to get up a little bit closer when there was something extremely significant to take a look at. So it has ranged from views of a foot away to 4 or 5 feet away.
Well, as you mentioned a model that you'd established for the number of expected meteoroid strikes and the number of expected space debris strikes. I didn't quite hear that and I wanted to double check. Was it about 1,000 meteoroid strikes and about 200 space debris strikes?
About 2,000 meteoroid strikes at a threshold of about 0.01 millimeter or centimeters, a tenth of a millimeter, and about 500 orbital debris strikes of that same size.
Okay, and then the second question is, when you do the chemical analysis of the space debris strikes, will you be able to identify, say, the difference between paint that came off of a Soviet booster versus a piece that came off of an exploded satellite? How detailed will those chemical analysis be?
Definitely not that detailed. Our primary objective will be to determine which are man-made and which are natural, and we will probably be able to go so far as to say, well, this is a paint flake, this is something from a solid rocket motor like aluminum oxide or aluminum structure, but even that's going to be difficult because we're impacting aluminum. Walker may have a comment on that.
I have a comment that one of the truly interesting scientific things that we can do with LDEF is to look at the chemistry of impacts on the backside, because there man-made debris should be essentially non-existent. We know the chemical composition of certain types of extraterrestrial materials, meteorites. We know very well what their composition is, and it's remarkably close, most of them, to the composition of the sun. Nonetheless, in this size range, there may be particles whose composition is quite different, and that we wouldn't know if we were looking at the front side or a random collection of stuff, whether it was extraterrestrial and with an unusual composition, or man-made, or something else. Whereas in the backside, if we analyze chemically the impacts, we can be quite sure that we're not dealing with orbital debris. We may well find chemical compositions and isotopic compositions that are quite unexpected and quite unlike those for the much larger objects that fall to Earth in the form of meteorites. That's an exciting thing to do.
Okay, we're going to switch back now to the Langley Research Center and let them try again.
This is Art Franklin from Wavy TV in Norfolk, Virginia. I'm at the NASA Langley. My question pertains to the information that we may receive from LDEF about building of the space station Freedom in the future. I know that it's going to be still several months before we get any detailed information about LDEF, but what do we know now that will really give us some definitive answers as to how to design or how to build the space station?
Well, I think in terms of atomic oxygen environment and what we've seen in the erosion of materials, our predictions seem to be on track there. So we will continue along the lines that we have been in looking at protective coatings for vulnerable surfaces relative to atomic oxygen attack. I think we need to examine thermal control coatings, look at our paints, see which ones are the more survivable, possibly look at some of the newer generation materials. It certainly brings together the synergistic effects of the space environment. In the laboratories, we never are able, of course, to combine all these environments, at least not at this point. So we have to see what the total environment means for these materials and look at that against what design requires for the space station. And of course, we're going to be heavily involved in that within the next year or so.
Hey, Bob, do you want to make a comment on that?
Yeah, I want to just make a very personal comment and tell you why I'm so happy that LDEF came back. One of the experiments that we, combination between Washington University and scientists at the University of Chicago, was selected to be part of the initial payload, attached payloads for space station on a thing called the Cosmic Dust Collection Facility. And there was a time when I didn't think LDEF was coming back. In fact, I made an announcement at a meeting once that Bill was there, and I said, well, I've written LDEF off the books. And he told me, don't be so hasty. There was a time when I thought the space station hardware design would be going forward at such a pace that even if LDEF came back, it wouldn't affect things. Well, the way things have turned out, LDEF has come back. The space station, as you know, is not proceeding as rapidly as we had hoped in the beginning. And therefore, that gives us time for our particular experiment to understand what happened on LDEF, and we're going to have to modify the design that we will have for our experiment. And without that experience, it would have been very difficult. We would have just gone ahead and designed it and put it up, and we would have had to have seen what happened. This way, we can really do it right.
Yeah, I'd like to add one other comment. You've heard a lot of people say what we see is in general the kind of things that people expect. Earlier this morning, I was in a meeting of probably several hundred materials people, and within that room there were expectations for almost anything you can conceive. I think the unique thing about LDEF is it has brought fact to this bit so that you have a way of judging what people predict. And so I think it's going to add a great deal of confidence in any of future designs.
I understand there's some questions from Marshall Space Flight Center, so we'll go there now.
To Dr. Whitaker, could you give me a count again of the modules that you found that were damaged, torn away, or in the bottom of the cargo bay?
We had 4 solar cell modules flying on AO-171, and we have 1 still in position on the experiment at this time. 2 were lost in space, and 1 was in the cargo bay, in reasonably good shape considering what he'd been through.
Could you have expected that after this long in space? And can you say, why was that totally due to atomic oxygen?
Yes, these modules were held in place by 2 mils of Kapton, mechanical attachment to the Kapton blankets. So we would have expected 8 to 10 mils of erosion of Kapton. So yes, we would have expected these to have been able to float away had they been disturbed.
This is Phil Schmidt from WAFF-TV. You keep talking about how important this is going to be for the engineers designing space station. I was wondering, have some of those engineers come forward and said, let me see what you've got, talk to me about the things you found on LDEF?
I presume you're asking me. Yes, they have. We're being a little cautious. We want to make sure we understand what's happening in these materials before we say you can depend on degradation due to ultraviolet radiation to bring about a change in absorptivity of material to a certain degree. But we're certainly going to respond as quickly as we can to their needs.
Yeah, I think it's fair to say there are lots of people who want to rush in and see LDEF. But as Ann says, we have to be cautious. The only people who really understand the experiments and the materials as they're being tested well enough to draw conclusions, I believe, are the principal investigators.
That concludes the questions from Marshall. Do we have any other questions here at Kennedy? Okay. If you did not get a chance to see LDEF in Safe 2 last Wednesday and take photographs today, there will be transportation outside for you to go immediately following the briefing. This concludes the briefing today on LDEF. Thank you for coming. Have a good day.